Hi, welcome to Physics for Engineers, and this is the continuation of Module 7, which is Dynamics of Rotation. So in this video, we are going to discuss the remaining module learning outcomes. So modules 1, MLOs 1 to 4 have been discussed on the previous video, so we're going to discuss the rest of the objectives. So first of all, let us discuss angular displacement, velocity, and acceleration. So to define this, the angular position, we choose a reference line in a rotating body. A particle P is located at the distance r from the rotation axis through O. So in this case, we choose the reference line as the line from the point O, which is the center of the rotating disk, extending outwards, and somewhere along that line is the position of the point P. So as the disk rotates, the position of the point P changes to this point. So the path that it traveled is the length S. So this length S is the arc length on the circular path of radius r, which is the distance between the point O and point P. The angular position of P is theta. So the arc length S is related to the angle theta through the relationship S is equal to r theta, in which theta is expressed in radians, which is equal to the angle in degrees times multiplied by pi over 180. So the angular position of the rigid object is the angle theta between the reference line on the object and the fixed reference line in space, which is often chosen as the x-axis. So by convention, our reference line is always the positive x-axis, and we measure in a counterclockwise direction. If we measure in a clockwise direction, the angle will be negative. So the angular displacement of the rigid object is the change in position of the particle in a rotating object, which is equal to theta f minus theta I. The average angular speed, or the Greek letter omega, is the ratio of the angular displacement of the rigid object, which is delta theta, to the time interval t during which the displacement occurs. So omega is equal to delta theta over delta t. And the instantaneous angular speed, or the exact speed of the object in a certain time, is defined as the limit of the average angular speed as delta t approaches 0. So omega is equal to limit of delta theta over delta t, which is equal to d theta over dt. So as usual, if we when we refer to speed, if the symbol for speed is just omega and no subscript of AVG, that means that the speed is pertaining to the instantaneous angular speed. Okay, so the average angular acceleration, represented by the Greek letter alpha AVG, is of a rotating rigid object is defined as the ratio of the change in the angular speed to the time interval delta t during which the change in the angular speed occurs. So alpha average is equal to omega final angular speed minus initial angular speed all over the change in time, or final time minus initial time, which is equal to delta omega over delta t. So the instantaneous angular acceleration is defined as the limit of the average angular acceleration as delta t approaches 0. So it is equal to the limit of delta t, this quantity, over delta omega over delta t as delta t approaches 0, or the derivative of speed with respect to time. So, imagine an object that undergoes a spinning motion such as its angular acceleration is constant. The equations describing its angular position and angular speed are analogous to those for the particle under constant acceleration model. So, if you can notice, this set of formulas are somewhat similar to those of the constant acceleration in linear motion. So, this is velocity. Final velocity is equal to initial velocity plus plus acceleration. So this should be alpha. Acceleration times time. Then theta f is equal to theta I plus omega I t plus 1/2 alpha t squared. Then omega f squared is equal to omega I squared plus 2 alpha theta f minus theta I. And theta f is equal to theta I plus 1/2 omega I plus omega ft. Okay. So let us have an example. So for our first example, we have a wheel that rotates with a constant angular acceleration of 3.5 radians per second. If the angular speed of the wheel is 2 radians per second at the initial time, which is 0, through what angular displacement does the wheel rotate in 2 seconds? Letter B, through how many revolutions has the wheel turned during this time interval? And letter C, what is the angular speed of the wheel at t is equal to 2 seconds? So, to solve this problem, let us use the formulas that we discussed earlier. So, an applicable formula will be, so we want the displacement and we have the speed and acceleration and time. So we can use this formula because we have the initial speed and acceleration then time, and we're looking for the angular displacement. So let us use that. So we have theta f minus theta I, which is just delta theta, is equal to omega I t plus 1/2 alpha t squared. So if you can notice, this is similar to the equation S is equal to VIT plus 1/2 AT squared. So that makes us easy to memorize. So substituting the givens, the known values that to solve for the unknowns, this is initial speed right here, then time 2 seconds plus 1/2 acceleration 3.5 times time squared, and that gives us 11 radians. But if we want to solve for the degree equivalent of that, how many degrees is that? So what we should just multiply this value 11.0 radians times 180 degrees over pi rad. Sorry, this should be here at the bottom of the equation so that the radians can cancel. So 180 degrees is equal to pi rad. So calculating that, we get 630 degrees. So the angular displacement is 630 degrees or 11 radians. But this should be the more proper solution, the radians, in terms of radians. Okay, so next question. Through how many revolutions has the wheel turned during this time interval? Now remember that one revolution is equal to 360 degrees. So since we already have the displacement in degrees, that is 360, we can just convert it to revolutions. 1 rev is equal to 360 degrees, and this gives us 1.75 revolutions. Then letter C, what is the angular speed of the wheel at t is equal to 2 seconds? So the angular speed of the wheel can be solved using this equation. Omega f is equal to omega I plus alpha t. So omega f, final speed, is equal to 2 radians per second plus 3.5 radians per second squared times 2 seconds, and that gives us 9 radians per second. Okay, so just a quick review. I have a table here which relates the rotational and translational quantities. Theta corresponds to S, or displacement. Omega corresponds to V. Alpha corresponds to AT, tangential acceleration, or circle tangential acceleration, or what is this? AC, centripetal acceleration. Then to convert theta into to convert the rotational quantities to translational, all you have to do is multiply it by the radius. So basically theta is equal to S, the linear displacement over R. Omega is V over R. Alpha is A over R. But AC is equal to V squared over R, which V is the linear speed and R is the radius. This one's different case. And I think we have discussed that on the previous video. So also, please take note of the rotational equations compared to the translational. You can see they are the same equation, only with different variables. So that's all you have to remember. Okay, so let's go to moment of inertia. Consider a particle of mass rotating in a circle of radius r under the influence of tangential force F and radial force Fr. Because tangential acceleration, there is tangential acceleration and radial acceleration in a particle that travels in a curve. So therefore, there must be forces acting on it, and the forces are Ft and Fr. So the radial net force causes the particle to move in a circular path with centripetal acceleration. The tangential force provides a tangential acceleration At, and Ft is equal to mat. So tangential force is mass times tangential acceleration. But torque is equal to force times radius, or force times distance. So we get mat times r. So theta, the summation of torque is equal to mr alpha, since tangential acceleration is equal to the angular acceleration times the radius times the mass times the radius. So grouping, ranging this equation, we have mr squared times alpha, and this quantity mr squared can be simplified into I, the quantity I, and this quantity is called the moment of inertia. So that our final equation here is torque is equal to the moment of inertia times angular speed. So notice that it has the same mathematical form as Newton's second law of motion. F is equal to ma. So notice the analogy, the similarity. Torque is equal to moment of inertia times angular acceleration, while force is equal to mass times acceleration. So in this figure, it is in the caption on the figure says that the tangential force on the particle results in a torque on the particle about an axis through the center of the circle. So examples of this are some practical examples of this situation are: number one, a bicycle chain around the sprocket of a bicycle causes the rear wheel of the bicycle to rotate. So if you can remember, if you can visualize that, we have the sprocket. So let me try to draw that. So this is the sprocket of the bicycle, right? So the chain is connected to your pedal, and as you exert a rotational force here in a pedal, you can the chain also exerts a force, a tangential force on the sprocket, and this force makes the produces a torque which causes the rear wheel of the tricycle to rotate, and thus you can move forward with the bicycle. Another is an electric dipole moment in an electric field rotates due to the electric force from the field. Another is a magnetic dipole moment in a magnetic field rotates due to the magnetic force from the field. And Lastly, the armature of a motor rotates due to the torque exerted by a surrounding magnetic field. Okay, so this is a cheat sheet. You can use this to as a reference to easily know the formulas for the moment of inertia for basic shapes. So m is equal to mass and r is equal to radius. So for cylindrical shell, the moment of inertia is mr squared. This is the easiest one to remember. But how about the more complex ones? So this one is actually used very frequently in example. So a long thin rod, the moment of inertia of a long thin rod with the rotation axis through the end is equal to I is equal to 1/2 ml squared. Okay, so I hope that you can use this sheet as a reference in the future. So let us have an example. So in this example, we have a uniform rod, just like this one. So a uniform rod of length L and mass M is attached to one end of a frictionless pivot and is free to rotate about the pivot in the vertical plane as shown. So this example or rotational reference line is this one, the pivot. So that is at the end of the cylinder. So that means that we are going to use this. We'll have to use this formula. The rod is released from rest and in its horizontal position like this. What are the initial angular acceleration of the rod and the initial translational acceleration of its right end? That means this end. So if you're going to calculate for angular quantities, you don't need to know which part of the object that you are referring to, because the object moves as one, it rotates as one. But if you are going to deal with the translational acceleration, of course you will have to need the distance L. Okay, let's proceed. So for the solution, remember that torque is equal to force times radius, and this quantity torque is also equal to the angular acceleration times the moment of inertia I. So from our formula earlier, the moment of inertia of this rod is 1/2 ml squared. And Fr, the torque, is equal to mg, which is the weight of the rod, and the moment arm is L/2. So the mass is concentrated at the middle of the rod. So cross multiplying, this gives us alpha is equal to mgL/2 divided by 1/3 ml squared, and we can cancel some quantities here, m, l, and that gives us 3g/2l. So this is our angular acceleration. How about the tangential acceleration? So the tangential acceleration, as I have shown you earlier, you can get the translational quantities by just multiplying the angular quantities by the radius. In this case, our radius is L, this length. So AT is equal to L alpha. AT is equal to 3/2g because we cancel out L here. So this is our answer, 3/2g. Okay. So let's discuss the rotational work, energy, and power. So how if we can relate the motion of a particle moving in a moving in a circular path, that means that we can also correlate those formulas, those quantities, with work, energy, and power. So consider a rigid object O, rigid object pivoted at O. This is point O. So this object can rotate, and the pivot point, the fixed point, is this point O. Suppose a single external force P F is applied at P. This is point P, and we exert a force F. where F lies in the plane of the page. The work done on the object by F as its point of application rotates through an infinitesimal distance. ds is equal to r d theta is. So the work done on an object by F at the point of application as its point of application as the distance ds approaches 0 is equal to dw is equal to fds. Work is equal to force times distance, and our distance is ds. And remember that work is equal to f sine theta, f sine phi in this case, times r. So which one is r? F sine theta r. This is r d theta. R d theta. Okay. So this gives us the quantity of work, which is equal to the torque. See this quantity is just the torque times d theta, the differential d theta, the differential of the angle. Oh, I see. Then in differentiating both sides with respect to time, dw over dt is just equal to power, and d theta over dt is equal to angular velocity. So that gives us the value P is equal to torque times the angular velocity. So we have derived the equation for power. How about work? So we know that torque is equal to moment of inertia times acceleration, the angular acceleration, and this can also be expressed as dw over dt. So using the chain rule, because I want the denominator to be d theta and not dt, so I will multiply d theta over d theta in this side of the equation. That's just equal to 1. So distributing, I have d it's this d omega over d theta times d theta over dt. So I can just simplify this quantity as omega. And since t is equal to since torque is equal to d torque times d theta is equal to work. So which one is that? If I cross multiply, if I transfer this to the left side of the equation, this becomes torque times d theta. So I have d theta, torque times d theta, which is equal to dw. I can have dw is equal to I times angular acceleration, angular velocity times d omega, and integrating this side of the equation so that I can get w. We have the integral, work is equal to the integral of I omega d omega from the initial velocity to the final velocity. This gives us 1/2 omega I omega I omega squared minus 1/2 I omega I squared. So this is called the work kinetic energy theorem for rotational motion. So basically, work is just equal to the 1/2 I times the omega f squared minus omega I squared. This is similar to 1/2 mv squared, right? So this, you can also use this for kinetic energy. So I have a sheet here which correlates or the rotational motion and the translational motion quantities, just like the earlier example, but with more coverage. So I hope you can also use this in the future. So how about combined rotation and translation? So when does this happen? So this happens during plane motion, or motion where a spherical object rolls around rolls on a flat surface. So this is basically called the rolling motion. So the kinetic energy of a rolling ball or other rolling objects of mass m is the sum of the rotational kinetic energy about an axis to its center of mass and its translational Ke of an equivalent point mass moving with the center of mass. So basically, in rolling motion, the kinetic energy is equal to 1/2 I omega squared, which is the kinetic energy of rotation, plus 1/2 mv squared, which is the kinetic energy of translation. And angular momentum is a vector quantity with a magnitude I omega and is directed along the axis of rotation. If the net torque on a body is zero, its angular momentum will remain unchanged in both magnitude and direction. This is the law of conservation of angular momentum. And lastly, for angular impulse, the angular impulse has a magnitude, the torque times time, which time t is the time during which the constant torque acts on an object. In analogy to the linear case, the angular impulse, I forgot what this Greek letter is, but this is torque times t on a body causes a change in angular momentum of the body given by I omega f minus I omega I. So torque times time is equal to the change in I times omega f minus I times the change in angular velocity. Then for the parallel axis theorem, so I just need you to be familiar with these concepts. So the parallel in the parallel axis theorem, the moment of inertia I of a body about an axis parallel to an axis to the center of mass is I is equal to ICM plus MH squared, in which I is the moment of inertia about an axis to the center of mass, M is the total mass of the body, and H is the perpendicular distance between the two parallel axes. So basically, the parallel axis theorem is just a formula for transferring the moment of inertia to a desired axis that we want, because in our formulas here, all of this have an axis which is at the center. So what about if you need to find the moment of inertia in this part, in this corner, or at the bottom, or somewhere else? So you can use this formula, which is the parallel axis theorem. Okay, so another cheat sheet. So that would be all for today. Thank you for staying with me. So in our next lesson, we are going to discuss, I think, waves. So until next time.